You can start maybe.
Yeah, okay. So can you all hear me?
Yes, yes.
Yeah, okay. So welcome everyone. Especially I welcome our today's speaker, Fang too. She is from Louisiana State University. She has done her PhD from Taiwan, and she is now an assistant professor at Louisiana State University. Her research area, broadly speaking, is number theory, but she works in hypergeometric functions and automorphic forms. I welcome you. And today she is going to speak about supercongruences for rigid hypergeometric Calabi-Yau threefolds. So over to you, Fang Ting.
Okay, thank you. Thanks for the introduction. And I would also like to thank the organizers for the invitation to speak here. Today I will talk about my joint work with Ling Long, Noriko Yui, and Wadim Zudilin. So first, the supercongruence in this talk is a congruence relation which is stronger than what the formal group rule can apply. So a typical example, and we will focus on the hypergeometric Calabi-Yau threefold. A typical example is like this, is a congruence like this. So first we have a kind of a finite sum here, which is coming from the truncated 4f3 functions. And this sum is congruent to the piece Fourier coefficient of the waveform level 8 module form when mod p cubed. Yeah. So here the notation here, the eta tau is the Dedekind eta function. So in our talk, we will focus on some supercongruence like this. Yeah. The Calabi-Yau threefold that I mentioned in this case, basically their p-adic differential equation are hypergeometric. So, and we will do point counting on this Calabi-Yau threefolds. So when we do point counting, we will use the hypergeometric type of carrier sum to get the information on the Galois representation, and also from the modularity of Calabi-Yau threefold modularity of rigid Calabi-Yau threefold defined over Q. Then we can relate the Galois representation to the Galois representation of a certain waveform Hedge eigenform. Yeah. So putting all this together, which will give us some clue to confirm the supercongruence conjecture given by Rodriguez-Villegas in 2003. So in this talk, I will first recall some background, but for more details or some history introduction, you can find in previous talk given by Boykers, Rodriguez-Villegas, Whicher, and also Yui talk. Yeah. So in the following, first I will give an overview about hypergeometric functions in different settings, which I will use in this talk, and then I will talk about a little bit of supercongruence. Yeah. So first of all, the hypergeometric function is defined as this formal power series. So, and in this talk, we will focus on the parameters AI, Bj are rational numbers. So the notation here, A sub n are so-called rising factorial or Poheven symbol, and they can be written as a gamma quotient. And as a function of z, okay, this power series satisfies an order NODE, which is a function equation with singularities 0, 1, and infinity. So let's look at our baby example, which you also mentioned in Fernando's talk. So if we consider the Legendre elliptic curve, the p-adic differential equation of this elliptic curve is a second order hypergeometric differential equation. Its parameter is 1/2, 1/2, and 1. So the period of this elliptic curve is this integral, and which is the integral representative of the 2f1 function times the transcendental number pi. So if we look at the data function of this elliptic curve, so if we do point counting over finite field, p, the number is equal to p plus 1 plus some this caret sum. So here, phi is the quadratic caret, which is the classical Legendre symbol. Yeah. So if we let AP lambda to denote these numbers, so we know that the AP is the trace of Frobenius of the associated Galois representation. And also from the modularity theorem, we know that for a fixed lambda, the AP value gives us the Fourier expansion of a certain way to cast form. If we look at the p-adic version of this identity, so when mod p, this finite sum can be written as this finite sum. Okay, so we have the AP is congruent to this finite sum with mod p. And this finite sum is the partial sum from the 2f1 function truncated at this term, p minus 1 over 2. So we see, so from this example, we see here we have the original 2f1 function and their finite field analog, and also the truncated version like this. So in general, if a abelian variety, its Pisolkar's differential equation is a hypergeometric, then which means that its periods can be expressed in terms of the classical hypergeometric functions or their logarithmic. Yeah, and in this case, we can use the hypergeometric type caret sum to get the information on their Galois representation for L functions. And so if we consider the p-adic version, so we can relate this hypergeometric caret sum to truncated hypergeometric function. More precisely, the caret sum can be expressed in terms of Gauss sum or Jacobi sums. So we can use Gauss-Colbreth's formula to relate the Gauss sum to the p-adic gamma function. Yeah, and in some cases, for ordinary pi p, so we can relate. We can also use truncated hypergeometric functions to get the L functions through p-adic, through the works p-adic unit root theory. Yeah. So this is kind of some relations among the original hypergeometric series and their finite field analog hypergeometric caret sum, and also its truncated version. And moreover, in particular, if the Galois representation is modular, then we can relate the Galois representation to center module forms. So this gives us, so from this bridge, we can link the coefficients of module forms to the Galois representations, and also we can link the coefficients to truncated hypergeometric functions. So this is kind of where the supercongruence comes from. Yeah. So okay, in this talk we will focus on hypergeometric Calabi-Yau threefolds. So, and we will focus on their Galois representation side, and also the modularity, which has been confirmed. Yeah, and we will relate the coefficients of waveform Hague eigenform to the truncated for the three hypergeometric functions. Okay, so I hope this gives you a picture about among all the relationships between the different versions of hypergeometric functions. Yeah, and now I will talk about the supercongruence part. So the supercongruence were first observed by Boykers in the combination of upright numbers, which is used in the proof of the irrationality of the Riemann data value, data 3. Yeah, so he proved that when n is equal to p minus 1 over 2, then this absolute number is congruent to the p's coefficients of this Hecke eigenform when mod p. So this form is we have seen in the beginning. And he also conjectured that this congruence holds when mod p squared. So for this congruence mod p squared, it was proved by Argo and Ono, and their idea is to do point counting on this Calabi-Yau threefold. And for the modularity part of this threefold, it was first proved by Gimon and Nigar. And also Argo and Ono themselves also give a straightforward proof to confirm the modularity of this Calabi-Yau threefold. And later on, Thielman extended this congruence to this supercongruence, which I showed in the first slides. Yeah, this supercongruence was first confirmed, first conjectured by Benhawa. So, and another example, let's look at the quintic threefold. So for the Calabi-Yau, for the quintic threefold, this is a family of the quintic three equation of the quintic threefold. So and these are their mirrors. So if we consider the Pisolkar's differential equation, they are given by the differential operator. So which means that they are hypergeometric, and the parameters are 1 fixed, 2 fixed, 3 fixed, and 4 fixed, and lower parameters are 1. So when lambda equal to 1, the mirror is modular. So we can identify the corresponding waveform Hecke eigenform. Okay. So and also McCarthy confirmed the corresponding supercongruence for this case in 2012. So in general, for the hypergeometric Calabi-Yau threefold defined over Q in this talk are the one parameter family of Calabi-Yau threefolds, and their mirror is Z. And the Pisolkar's differential equations are arising from these 4f3 hypergeometric functions with lower parameters of 1, 1, 1, 1. And the upper parameters are D1 1 minus D1, D2, 1 minus D2. And the D1, D2 are a pair coming from this set or any of these 4. So the total, we have 14 cases. So for these mirrors, for generic lambda, this is their Hodge Diamond. So H21 is equal to, their H21 and the H12 are equal to 1. But when lambda equal to 1, the H21 is equal to 0. They are rigid. And the error function of the third eta cohomology is of this form. Okay, this form. So, and from the modularity of rigid Calabi-Yau threefold defined over Q, we know that, okay, for these error functions, we can find a waveform module form such that the L80 Galois representation arising from this third eta cohomology group of this mirror is isomorphic to the L80 the Ling representation associated to this waveform Hecke eigenform. So, and so this is kind of some background about the Calabi-Yau threefold family. Okay. And for the supercongruence, it was first conjectured by Rodriguez-Villegas. He numerically identified the corresponding Hecke eigenforms for each of these 14 cases, and he conjectured that the truncated 4f3 hypergeometric function is congruent to the coefficients of the corresponding Hegel eigenform when marked p cubed. Yeah. Okay, so our work is to confirm Rodriguez-Villegas supercongruence conjecture. So we in this joint work, in my joint work with Long, Yui, and Zudilin, we give uniform proofs to verify the supercongruence for all the 14 cases. And okay, I want to point out that actually 3 of them was proved before 2016. As I mentioned before, the one half case was confirmed by Kilburn, and 1/5, 2/5 was confirmed by McCarthy. And McCarthy and Supriya, they further confirmed the case 1/2 and 1/4 in 2016. So the strategy of our proof are we will first consider the hypergeometric carrier sum to get the Galois representations, and then we use Gauss-Corbry's formula to relate the Gauss sums to p-adic gamma functions, and using a p-adic analysis, we can link the supercongruence. Sorry, we can link the truncated 4f3 functions to the coefficients of the waveform Hegel eigenforms. Yeah, and also for the ordinary price case, we can use the works unital theory to check the supercongruence. So in particular, in our case, we use hypergeometric motifs to describe the arithmetic background, and then we use the two different approaches to get the supercongruence. So we break the supercongruence into a major term and some error terms. And as I said, the first approach is using the work unital theory for ordinary price case. And the key point will be using the relation between the gamma function and the p-adic gamma function. And second approach, we use the finite hypergeometric function introduced by Villegas, Cohen, and Mallet. And then we will use the Gauss-Corbry's formula to relate this carrier sum to the p-adic gamma function. Yeah. Okay. And for shorthand, for convenience, I will use BCM to denote the work by Villegas, Cohen, and Mallet. So once we use the carrier sum or the work unital theory to get the supercongruence with the major term and the error terms, the next step is to eliminate the error terms. So in this step, we will use Zudilin's residue sum method plus some p-adic perturbation to kill all the error terms. Yeah. So this part, but in this talk, I will mainly focus on BCN's approach. And if I still have time, I will briefly mention the works unital approach. And we believe this method is new. Okay. And again, if I still have time, then I will talk about a little bit how we use the residue method to kill the error terms. And another thing I want to point out here is that in a very recent work by Michael Allen, he proved the 4f3 supercongruence conjecture by Ling Long. The case he considers is the 4f3, who's like this form, but the lower parameters are not 1, 1, 1, 1, but some other parameters. But in this case, their hypergeometric data are also certain. The 4 and 3 are coming from certain hypergeometric data defined over Q. Okay, so hypergeometric data. Okay, so as I mentioned, the hypergeometric data here, I recall the definition about hypergeometric data. Okay, so a hypergeometric data is consists of two multi-set alpha, beta, and z. So they are keep in mind the alpha set are collating all the upper parameters arising from the hypergeometric F series, and the beta are the lower parameters. But we will require that AI, BJ are not deferred by integers. A reason is because that if they differ by integer, this hypergeometric series can expressed in terms of a lower order hypergeometric function and its derivative. So, and also if when we look at the finite hypergeometric function, you can see some cancellations. We can also see some cancellations arising from AI, BJ if they differ by integer. Okay, so and a multi-set alpha is said to be defined over Q if the coefficients of these polynomials are integers. Okay. And a hypergeometric data is defined over Q if all the alpha, beta, and z are defined over Q. And in this special case, BCN give a recipe to construct a model associated to this hypergeometric data, and their data function can be computed using their finite hypergeometric functions. As using in Fernando's talk, actually, he used the Magma to perform some numerical data to compute error functions, which is also based on their algorithm. Okay, so for BCN's finite hypergeometric function, so here is something out about the finite hypergeometric function. So basically, we will consider the group homomorphism from the multiplicative group of finite field to the multiplicative group of complex numbers. So, and for this group homomorphism, we say that they are multiplicative carets on FQ. And as usual, we will put a hat on the multiplicative group to denote the group of the carets, of multiplicative carets. Okay, and for a caret chi, we will use chi bar to denote its complex conjugation, and it is equal to its inverse because the caret value are all root of unity. Yeah, and for convenience, I will use epsilon to denote the trivial caret. Okay, so for a hypergeometric data, so we'll consider the finite field whose characteristic is co-pi to the least common positive denominator of all the parameters AI, BJ, and T. And when we require Q congruent to 1 mod M, then we can so this restriction is to make sure that the Q minus 1 times the AI is an integer, and so is the Q minus 1 times BJ. And so we consider such a finite field. So we fix a generator of the multiplicative group. Okay. So for convenience, we let capital AI to be the caret arising from the upper parameter AI, and BJ is the correct B. Okay, Bj be the character arising from Bj be a character arising from the lower parameter Bi. Okay, so you can see here the capital A, the character is a finite field analog of the rational number A. Okay, so another way you see that we can see is that if we, so for this one x to A, if we fix the exponent A, and when x varies, so this one gives us a multiplicative function. So the multiplicative character here is the finite field of this function. Okay, and for the Gauss sum of the multiplicative character defined in this way is the finite field analog of the gamma function, the classical gamma function. Yeah, so as you see here, the S to A is a multiplicative function, and exponential is an additive function. So on the finite field side, we have a multiplicative character and the additive character here. So this is I kind of give us a dictionary to define the finite field analog of the hypergeometric functions of a finite field. So okay, so using the Gauss sum, BCN define the hypergeometric function HQ in as follows. So you can see this one is exactly the exactly the same thing as our original F function, hypergeometric functions. So if we use, okay, this is the original definition of the hypergeometric function. So if we write the rising factorial in terms of gamma quotient of this form, and then we apply the reflection formula of the gamma function, so we get the F functions of this form. Okay, so and this part is coming from B1 here. Okay, and this part coming from upper perimeter. This part coming from lower perimeter. So the finite field HQ function here is first we summation all the possible K here, but we do a normalization marked out by the size of FQ star. Okay, and this part is corresponding to B1 here, but of course we apply a reflection formula of Gauss sums. Okay, and then the second part again coming from the upper perimeter, which are the parallel to this part, and the third part, this one, are parallel to this part. So as I mentioned before, for the finite field analog of the integers are trivial characters, and the finite field analog of minus Bj are the inverse of the capital Bj. So this is as you can see here, they are exactly the same thing, and the rest part is for the character values here. Okay, so this is the BCN's hypergeometric functions. Okay, but notice here that for given hypergeometric data, we will require the finite field, the size Q is congruent to 1 mod M. But when the hypergeometric data is defined over Q, then we can drop this restriction. Yeah, so which means that HQ function can be defined over all the FQ. The idea is that we can use the multiplication formula for Gauss sums to get rid of the primitive character of some order n. Yeah. So, the multiplication formula of Gauss sums is also known as a Hudson-Davenport relation. They are the finite field analog of the multiplication formula of gamma function. Yeah. So here I will, okay, let's look at some example. So here, for simplicity, I will let chi to be any caret and the eta n be a primitive caret of order n on the finite field FQ with the Q congruent to 1 mod n. So to make sure that we have a primitive caret of order n. Yeah. So under this setting, we can rewrite this constant eventful relation into this form. Here I move the part arising from trivial caret to the right hand side. So okay. Anyway, we have this is our product multiplication formula. So for example, when the set is equal to 1/3, 2/3, the corresponding product, okay, original corresponding product of this one, but apply the multiplication formula, we can get a g chi cube over g chi and times the value here. So you see here on the right hand side, we don't need all the 3 characters here. So similarly for the multi-set arising from 5, we have a similar expression on the right hand side to get rid of all the 5 characters. So for composition numbers, like for example, like 1/4, 3/4, we can apply the multiplication formula, and so we can get the g chi 4 over g chi square and times some character value here. And similarly for 1/6 and 5/6, we have this expression. So you can see from here, if we have a multi-set divided over Q, so the expression is basically coming from the divisor of the denominator, and also the value of the previous functions like this. Yeah. So this is the idea how to define the HQ functions when a hypergeometric data is defined over Q. So in BCN's work, they give a precise definition about such HQ functions, but I will skip here. The definition here. But here are some examples. So the first one is the Legendre elliptic curve case that we have seen before. So in this case, the corresponding hypergeometric data is 1/2, 1/2, and 1/1. So their trace of covariance is given by this HP function. Yeah. And another example is that if we consider the family of the elliptic curve, which is corresponding to the congruence of the group gamma 0, 3, so their corresponding hypergeometric data is 1/3, 2/3, and 1/1. So due to BCN, we know that for almost all pi p, and the number of rational point over FP is equal to p plus 1 minus this HP functions. So, and this is defined for all prime p. So, okay. Any questions so far? Okay. If no, then okay. Next, I will give an example to demonstrate how we prove the supercongruence for the rigid Calabi-Yau threefold. So here I take D1 and D1, D2 are 1/3, for example. Yeah, okay. Okay, so from the follow BCN, we can construct the model corresponding with the hypergeometric data, which is defined by these equations. You know, they are again, which is a rigid Calabi-Yau threefold. Okay, and if we do point counting on the non-singular completion of this model, the number is equal to some polynomials in Q and minus the HQ value. And as I mentioned before, because this hypergeometric data, okay, this one is defined over Q, so we can, so this HQ is defined for all FQ, and we can use the multiplication formula to combine all the Gaussians. Okay, so HQ value is written in as this form. Okay, and yeah, okay, so for the G chi bar here are coming from the lower perimeter 1, 1, and the G chi 3 and G over G chi times these carrots are coming from 1/3 and 2/3. Yeah. Okay. So from the modularity, we know that okay, this when HP value is equal to P plus P's Fourier coefficient of the corresponding waveform eigenform. Yeah. Okay. So now we are almost. So this is our first step, and we get the HP function, the relation between the H value and also the module forms part through the modularity. So next step, we will use the Gauss-Corbis formula to rewrite HQ value or HP value in terms of p-adic gamma function. So the idea is to use the Gauss-Corbis formula. Okay. If we fix omega to be a generator of the multiplicative group, so the Gauss, and also here pi is a fixed root of this polynomial in CP. Okay, so Gauss-Corbis formula tells us that okay, the Gaussian of this guy is equal to the p-adic value and also plus some additional p part. So from here, from this formula, we can write the Gaussian, the quotient of Gaussians in terms of p-adic gamma functions here, and also some additional p part. Okay. Yeah. And the practice notation here is the fractional part of the number x. Okay, so now we have the relation between H functions and the p-adic gamma functions. So next step, we will use the p-adic analysis to kind of decompose, to break up this part. Okay, so before that, let me briefly recall what the p-adic functions and some nice property about p-adic function. Okay. So for a positive integer n, then we define the p-adic gamma value of n in this way, and notice that which is similar to the classical gamma function, but we will kick out the numbers which are multiple of p. Okay, and then we will use this one, gamma p values to extend the gamma p values to all p-adic integers by looking at by using the limit of all the gamma n values, which is close enough to the p-adic integer x p-adically. So okay. So you can see here the p-adic gamma function is the p-adic analog of classical gamma functions. So similar, parallel to the classical case, they satisfy the reflection formula, multiplication formula, and also some other nice properties. But one of them, which is very important in our work, is the Taylor expansion. But for our purpose, we only need the first 3 terms. So I listed this congruence relation. Okay. So if we consider the p-adic value of A plus SP, where AX are all p-adic where AX are p-adic integers. Okay, then so this guy is congruent to, okay, when mod p cube, this guy is congruent to gamma pa plus gamma pa times some xp part, and also gamma a times some xp squared part. And here G1, G2 are the derivative of gamma p-adic gamma function. Okay, so use the expansion here, we can rewrite our actual values in terms of some p-adic gamma functions. And again, use the definition of the p-adic gamma function, we can find that this is the actual value is congruent to this finite sum times some other terms and plus some other terms. And here J1, J2 are some expression involves the G1, G2 functions, but they are important in our work, but not important in this talk. So I was given an expression here. Yeah. But anyway, so this part is just to follow the Taylor expansion, and we can get the congruence relation here. So okay, so from here, after a few pages of calculations, we end up that the actual value is congruent to this finite sum plus some error terms. Okay, so we almost there. So combined with the modularity theorem, we know that the AP value is equal to actual value minus P. So which means from this congruence relation, we know that, okay, AP is congruent to the 4f3 truncated hypergeometric function is 1 plus some error terms. Okay. So the goal is to kill the error terms. Yeah, but still, after a few pages of calculations, if you believe us, okay, so we can check that the C1 is congruent to P and C2 is congruent to P minus P squared. So, which means the left-hand side of this equation, congruence relation here is H minus P here, when mod P cubed. Yeah, so which means the AP value from the modularity theorem. So AP value is equal to H minus P, and which is congruent to this guy mod P cubed. So which means the AP value is congruent to this truncated hypergeometric function when mod P cubed. So yeah, so in other words, first we use the BCS carrier sum formula to compute the Galois representation, and from the modularity theorem, we know that the HP value, we know the exact relation between the H value and the coefficients. And then we use Groskovitz formula to rewrite the HP, but yeah, the H value in terms of p-adic gamma functions, and then use the p-adic analysis, we can get the supercongruence relation like this. So this is the idea that, so this is the idea how we prove the supercongruence. Yeah. So for all the 14 cases, okay, so please just look at the highlight part. So for the 14 cases, so for the given hypergeometric data, actually, for each of them, there exists an allocated degree 3 Galois representations associated to the given hypergeometric data, and the Galois representations on the cyclotomic field, and this n is depending on the common denominator of D1 and D2. Yeah. So, and okay, Yeah, and this Galois representation is unrealized almost everywhere, such that at each point ideal of this ring with known Q with the size of the residue field. Yeah. Then the trace of the Frobenius of this Galois representation is equal to HQ value. Okay. And in particular, in this case, this degree 3 Galois representation decomposed into two sub-representation of degree 2 and degree 1. And moreover, because the hypergeometric data is defined over Q, so due to the work, due to BCM, we know there, so this Galois representation can be lifted to GQ. And for the Galois representation arising from BCM, the trace is equal to the value HP for OP. Oh, I forgot to mention that. Sorry. The first for the cyclotomy field case, this is original from cats, and for the BCM, so the BCM tells us for the HD defined over Q, this Galois representation can be lifted to G2. Yeah. So okay. So based on the results of KBCM, so sorry, BCM for all 14 cases. So we can see that okay, the trace of Frobenius of this Galois representation of GQ is equal to this HP, and from the modularity theorem, we know that okay, this HP is equal to the fixed Fourier coefficients of the associated waveform Hagen eigenform and plus another part. Okay, and here chi HB is a dirichlet current of all at the most 2 come from some Legendre symbol. Yeah, and they can be explicitly determined depending on the choice of D1 and D2, but I skip the expression here. And notice here that, okay, so this part is the corresponding to the degree 1 sub-representation that I mentioned here. And for the two-dimensional representation is this one. Okay, yeah. So this is one of the key points in our to prove the supercongruence conjecture. And again, as I said before, then we will use Galois-Copi's formula to reduce the supercongruence. Then we get the major term and the error terms. And although I didn't mention before in my example, but in this paper, we give a systematic way to kill the error terms, which works for all 14 cases. So we use the residue sum method and the p-adic perturbation to handle the error terms systematically, or we do not handle them one by one. Okay, so but for these cases, we will follow the works dash operator to do the p-adic analysis. Yeah, and okay. Okay, I think I will stop here. Yeah, thank you very much for your attention. Okay.
Thank you so much. It was a very, very nice talk. Thank you so much for your time. So let's just see if there are any questions. Devendra, are there any questions?
No, not on YouTube.
Not on the YouTube. Okay. So Professor Philip, Professor Noriko, Professor Ling Long, if you have any questions.
No, I'm a co-author of the paper, so I know.
Yeah,
everything.
I know. Of course.
Yeah, so because you should mention once that you are doing all this arithmetic stuff on the mirror Calabi-Yau, not on the original one.
Yeah. We are doing.
Parameter is lambda, so this entire thing is done on the mirror side.
Yes. Yeah, I forgot to mention that. Yeah, wait. Okay. Yeah, like the model that I mentioned here, they are actually the middle. It's a middle.
Mirror side. All calculations are done on the mirror side. That's when you have the rank 4 motif. That's why it's easier.
Yes.
Okay.
What does the rigidity means here exactly?
Pardon?
Rigidity?
Okay, rigid means. Where is my definition?
Diagram. Yeah.
The rigidity means H21 equal to 0.
Okay.
The Hodge number H21 equal to 0.
So if you go to the mirror side has a 1, 1, 1, 1.
Yeah, for generic this one.
Yeah. But somewhere called that conifold point, this degenerates to 3. Sometimes degenerates to 3, not 4.
Okay, Devendra, any other questions?
No.
Okay. So I think we have no more questions. So we all thank you again. Thank you for your time, and thank you to be part of this year-long program. So Devendra, you have something
Thanks
to
to you
add?
also, Supriya, for chairing this talk actually. And
Oh, it's my pleasure.
so yeah, we will be.
How the seminar will go on?
Hello.
So yes, this is a year-long program.
Yeah, you don't have any vacations?
Seminars. There was some vacation now at the end of the first and second trimester.
Yeah, but then here in Canada, it's July and August, the sort of vacation. So I cannot come to all talks in August, for instance.
Okay. Yeah, we are aware that that is July and August is the vacation in the West, Europe also, and Canada and America. That is why we started it on the 1st September.
Okay. So I think Devendra, so you can end now the meeting.
Okay.
So
thanks,
thank you, Fang Ting too.
And thanks to Priya to you.
Thank you.
See you next week.
See you. Okay.
See you. Good night. Bye.